The new groups in our new seating chart have just been working on this in the back of their homework spirals. And I'm going to start going piece by piece and see if they agree, disagree, what they got, what they didn't get, or maybe if they had any other ideas than I had. Okay, that was to the mic, now to you guys. I would go 1 over cosine. You guys agree? And actually, this one ended up being quite nice because what's true about both those denominators? So I can put it together, right? Squish, that's a very mathematical, but correct term. Good job. Now, who thought to multiply? Multiply to both sides? Oh, you could have done it that way too. So I would multiply. I think that's okay. I don't know if you'd want to split up because that's just what happened. You could have squared both sides up here. You could have done that. Or you could multiply. I heard different people saying squared, so I'm kind of going off of what I think you wanted to do. Matthew was very honest, and I think it's very helpful. He was like, I kind of just stopped there. Who kind of agrees? Oh, right. So I knew that he kept thinking, but isn't this where a lot of people, at least initially, kind of slowed down and got stuck a little bit, right? So he's trying to think through different actual angles in the unit circle, like when will 1 plus sine equal cosine? It's really hard to look at an equation and just try to, like without there being a trig equals a number, like cosine of x equals 1/2, or sine of x equals negative root 3 over 2. Without having something concrete, it's really hard to come up with. Is there anything else that can transform?
Yeah, you could,
What are you thinking, though?
I was thinking to divide 1 plus sine by sine, and then you would get 1 equals cotangent, but that's not right.
Right. And you would divide both. So what do you think? Good idea, though. Right lines of where I'm going to go. He's thinking, why don't we multiply by 1 minus sine of x, which is something that we did in t-proofs. Which we did in t-proofs in order to try to get a difference of squares, because he's thinking, I like 1 minus sine squared. I don't like this. We can get it. So he's thinking along the right lines. But the problem is, if we multiply that here, times 1 minus sine x, and if we do another one that goes over there, this one will be great. 1 minus sine squared will be cosine squared, but what's going to happen over here? We're going to have a cosine and a sine still. So I think what I would do is what some of you guys were thinking, but not quite knowing how to go about it. I would square both sides. But we have to do it legally. And legally says, don't kill a puppy. Legally says you got to FOIL. And in FOILing, you would get 1 plus 2 sine of x plus sine squared of x equals cosine squared of x. Why did that just make things a little bit better? Say it one more time, Joe. No? You could subtract the cosine squared x, but I might not do that yet until I think about how cosine squared can be rewritten as, why would I do that? Stuff can combine now, right? As soon as I get it all in terms of 1, sine and sine squared, okay, it's still kind of messy, it's going to be a quadratic, but at least it's all sines. Maybe I can factor? Yeah, when you add sine squared to the other side, you will have, I'm going to write it in descending order like we like all of our quadratics. So plus sine squared, I'm going to have 2 sine squared. So 1 plus 1 will be 2, but I have more. I'm also going to have my plus 2 sine of x. So I have him, and I have 1 plus 1 to make 2. And I can subtract my 1 also. So what I did is I changed cosine squared. I moved all of that to the other side, and in essence, I ended up getting a 1 plus 1 sine squared. I still had my plus 2 sine, and then my 1's ended up canceling.
Now you can factor out.
Now I can factor. Are we okay, though, with what I've done so far? Getting to here was all like transforming with 1 over cosine and multiplying. Squaring both sides kind of opened up the door if I did it legally, because all of a sudden I can transform 1 minus cosine squared, moving it all to one side to get equal to 0. And then as I think Jason just said, factor. Oh, 1 sine of x, sorry. There's another sine left. Took away 1 sine, but I had 1 left. One of the most common mistakes in factoring out GCFs is if everything factors out, there's a 1 remaining. Gotta hold the place. But what do I do once I have factors equal to 0? Set both equal to 0. So I can say either equals 0 or sine x plus 1 equals 0. To be honest, Matthew, if I was going off your route earlier, 1 plus sine equals cosine, in my head I actually kind of thought, is this an impossible problem? Cosine can't go over 1. That doesn't make sense. But then I had to think about, oh, sine can be a negative. That's super hard to think about. I don't know if I could have figured it out from here.
Start at pi 1 plus some 0.
Yeah? Yeah, so maybe you were able to find 1, which is good. In another case, if I was to have something like 1.3, then my head's just totally gone. You know what I mean? But the nice thing is there were some unit circle ones, as we're going to see here, there were some unit circle ones that definitely matched up. If I was just explaining in my head, just kind of creatively thinking through all the unit circle ones and ignoring all the other ones, it's really dangerous if you can't get it to actually be, oh, whew, something mathematical, something solid. Just a warning. Divide by 2. Guys, aren't we just looking for when sine is equal to 0? Or when sine is equal to subtract, -1. Matthew was just checking out his unit circle. Some of you might be pondering your unit circles. Sine, which is the y, or the 1, 2, 3, starts at 0. So 0 is 1. Pi is another. 2 pi is another. We could do this all day. Wait a minute, I think we need to think about directions. We will in a second.
0 plus pi.
Sine is -1. Well, if it starts at 0, it ends at 1. That's at pi over 2. Wait. -1. That's going to be at 3 pi over 2. Unit circle, what we're thinking about is sine's going to be 0 here and here, for all the pi's and 2 pi's, and it's going to be -1 down there. Those are my 3 locations. So how do I take those 3 locations and write an answer for all solutions? And I just crossed out the directions. For all solutions. 2 equations? Why equations? Because we're not listing them all out. No. We're trying to make an equation with an n to explain those 3 locations. Now, technically, some of you might be like, hey, they're 90 apart. That's true, but which 90 is missing? So I can't just say every 90. It's not going to work. None of those are included because it's only when sine is -1 that this equation is true. So maybe I should just start with this one, right? That would be x equals 0 plus, yeah, can I add pi and get this guy too? And then I'll keep on adding pi and getting back and back and back. Let's just add pi in. That way I get 2 and 1. Oh, hey, 0 plus pi n, isn't that just pi n? Nice. Starting at 0 and adding not 2 pi, but let's just add pi because the angle 180 apart is also an answer. So I'm just shortening my work. But who's the other guy that I need? But am I going to be adding anything to him to get anyone else? No. So I'm going to take the 3 pi over 2 and say, well, I'm not adding anyone else because there are no other locations. So just take him, and just taking him, I say him and all of his coterminals, so 2 pi n. So if you're dealing with just location, one location, 2 pi n's enough. But if you're trying to get more than one and you can see another solution 180 away, that's when we use the pi n. Did any of you guys look in the answers for some of the ones in the back of the book and see pi n's? It usually happened on tangents. Usually, whenever there was a tangent, pi n comes out. But this one, there was no tangent, and there's still an equation with pi n. My final solution? Written the easiest way would be pi n and 3 pi over 2. Joe, they aren't the same thing. Hold on, did I hear you wrong? What were you asking me? Oh, there is a, oh, you mean in the beginning problem. Got it. Sorry, I was thinking about the final solutions. My bad. I was thinking here, but he's right. There is a tangent in the beginning, which might have something to do with it. Whew. Was that an easy one? No. But why do we do it all together? Because I'm hoping we reviewed a lot of things that might be questions in homework. Color pens, let's go. Let's see. Color pens, let's go see how you guys did. I think I have the homework open right here. Check. And I have the solutions open right here. Uh-oh, extraneous came back to play. Extraneous happened with logarithms. When we ignore a log, sometimes we get an illegal answer that's impossible. Same thing with trig. Sometimes when we ignore trig or get rid of trig, we can get an impossible answer again. Just reminding you of the vocab extraneous. When you undo math, sometimes you forget that not all answers are legal for all types of functions. But let me go ahead and let you guys start checking. After extraneous, numbers 14 and 20. Number 20, they did it 2 different ways. You definitely did not have to do it 2 different ways. But you can check out, there are 2 different ways of solving it. This is one of those with the 3x. You should have looked at triple the answers. But in this one, it might not have made a big difference because it's all solutions. Take a second to contemplate. Both of these, the directions were all, which is why there are n's. Both of these, the directions were all, which is why there were n's. Remember from yesterday, if you have one of these, you just, in a sense, you can even in your brain, you can circle it and say, okay, I'm not allowed to go there. I'm not allowed to divide by 3. We have to do the tangent first. Does tangent ever equal root 3? Square root of 3 over 3, 1 square root of 3. Yeah, at pi over 3's. Oh, at pi over 3's. Which ones? The plus or minus, guess what it says about the quadrants? How many quadrants are you allowed to go to? All of them. So if you take pi over 3 plus pi n, you get the first quadrant and the third, I think, right? First and third. And then, oh, sorry, there were 2 answers, not 2 ways, 2 answers. You can do positive pi over 3. Ignore it, there's a box. You can do positive pi over 3 plus pi n, that'd be first quadrant and third quadrant. And then 2 pi over 3 would get you second quadrant and fourth quadrant. But there actually was a little bit easier way of writing it. Did anybody actually find a better way than even the book did? There's a little bit simpler way. Doesn't make a big difference. It's not like you lose points by not doing it. But if your locations are every pi over 3, couldn't you have done pi over 3 plus pi n and said, hey, that would work for you? Check, check. Or for, who's that guy? Isn't that negative pi over 3? You could be snazzy and do plus or minus and then get all the quadrants. But you could have written it separately. That's what they did. That's okay. But remember, it's 3x equals that. So how do I get x alone? Divide by 3. So when you divide by 3 and divide by 3, that becomes pi over 9. And this becomes n pi over 3 or pi n over 3 or pi over 3n. Lots of ways of writing it. Long story short, the pi gets over the 3 also with an n. Same thing here. we have to divide by 3. You didn't have to worry about that whole tripling the interval because there was no interval. It just said all. So we write out a little plus pi n and divide him by 3 too also. And can't do more synonyms. Okay, what's next? Oh, it was disgusting. Wait, think about our bell work. We don't want both of these guys, so who should we change? To be 1 minus cosine squared times 2. And then move it all to one side, and then factor, and then it's just like bell work, or at least really similar. But it didn't have as many steps. Sine squared could become 1 minus cosine squared. Then you would distribute the 2 into the 1 minus cosine squared, move them all to one side with them in descending orders. The 2's cancel, so just take out your common factor, each one equal to 0. Go look on your unit circle. Number 36. You had to do some plugging and chugging. But, okay, wait. There was a lot of math that happened. Can you guys tell me what happened in between this step and this step? Don't just copy them. They got a common denominator because this guy had sine squared over cosine. This guy was cosine over 1. They had to get a common denominator, which is where this guy comes from. Then you were able to, what did we say, smush it together? Squish. You were able to squish it together. Shout out. Squish it together. Then we multiply to the other side. Then we say, wait. What's cosine squared plus sine squared? It got so much easier. Cosine ends up being 1/2, which only happens at pi over 3 and 5 pi over 3 in the interval. Did you guys follow the one with 2x we did yesterday? Subtract, divide. Don't touch the 2x. What do you got to do first? Deal with the sign. When is sine? Oh, here, 4 pi over 3. Third quadrant, 5 pi over 3, fourth quadrant. It's an all solution one again, so just plus 2 pi n plus 2 pi n. There's no nice way to get from one to the other. They're not like 180 apart. There's no nice way to combine that. So divide by 2, it's going to be over 6, which reduces. 4 over 6 is 2 over 3. Have to divide him by 2 also, which is why it's only pi n. Divide by 2 over 6. Divide by 2, pi n. Anybody dislike number 60? What did the direction say? It actually didn't say use the graphing utility. Well, it did as like a last step. What did it say to use first? It's up to you guys if you want to do this in your notes because we've actually done this quite a few times. That's an example we didn't get to. Let's come back to him in a second. I'm just trying to throw a few hints in your notes. If you want to throw this in your notes, you totally can. If you don't want to, that's okay too. But whenever you see something like, and you guys try to do your x method and say multiply to 1 and add to 3, is it possible? No. Not with nice rational zeros. So instead, you have to do x equals negative b plus or minus square root b squared minus 4ac all over 2a. If you need to, this might be a good time to write this again in your notes and try to keep reminding yourself it's actually kind of important if you haven't figured that out yet. But here's the one thing that's extra, the one thing that's different. This is not just x squared. This is not just 3x. It's not even like e to the x. Wait, we did quadratics with e to the. And when we did it with e to the, we had to remember it's not just x equals who's being squared. When you plug into the quadratic formula, what normally is x equals, because normally it's ax squared plus bx plus c, you have to say who's being squared this time. So coming back to our homework problem number 60, very, very, very similar. You would have tried to do the x method. Nothing multiplies to be negative 12. That adds to be 4. And so they went ahead, and the directions told you. Use the quadratic formula using this A, this B, this C. It's all plugged in, simplifies down to be this guy, which actually square root of 64. Psh, I know him. So they went ahead and did -4 plus 8 over 6 and -4 minus 8 over 6 to get their two answers. But tangent equals one or tangent equals the other. But why on earth did they tell you to use your graphing calculator? Square root of 3 over 3, 1 square root of 3. It's not there! I need to use tangent inverse. Square root of 3 over 3, 1 square root of 3. It's not there! I need to use tangent inverse in my calculator to solve. Don't stress too much about needing to get all the way to the decimals in each of the individual answers. Those are the correct ones, but it's a little bit beyond our scope of what I would ask on a test as far as to finish this problem all the way to those. Number 86, did you guys figure out they literally just wanted you to graph both and say, hey, they intersect 3 times, aka there are 3 solutions, done. That's it. Intersect 3 times, 3 solutions, done. Number 94, was he the Ferris wheel? Oh, yeah, there he is. He's the Ferris wheel problem. They give you this example here, and they ask you a few details as far as when I think someone's at the top of the Ferris wheel. So you're going to be setting the whole thing equal to 53, because that's the... No, it's passing the middle. Is that what they're asking? Passing the middle? Ah, 53 feet above ground. If you guys remember your equation of a sinusoid, y equals d plus a sine or cosine b c x minus c over b. That's your sinusoidal axis. That's the middle of your circle or of your trig graph. So when it says when will it be 53 feet above ground, you can set height equal to 53. They're actually just asking you to solve. Plug in 53 and solve. And so when you do, you end up subtracting the 53s. They cancel. You get this equals to 0. Divide by 50. Think about sine. When is sine 0? At 0, at pi, at 2 pi, and then solve. Adding, multiplying by the reciprocal. You actually end up with 8 and 24, which are 12 apart? No. 14 apart? Nope. 16 apart. So I think it completes one full revolution every 16 seconds. Then they ask, when will you be at the top? We're going to be at the top when... Can you guys figure out how high off the ground the top of the Ferris wheel is using this equation? How high off the ground would the very top of the Ferris wheel be? How high would you be above the ground? $53 is the middle, because it's about which it's cycling. 53 is the middle, or the sinusoidal axis. How high, how low do you go from 53? What's the amplitude? I know it was last semester, but we graphed sines and cosines. Remember, that's the middle and that's the tippy top. So what's 50 plus 53?
103.
If you guys can't add those two now, I'm really scared. You're just not paying attention. What's 50 plus 53? 103. So when you're at the top, guess what you set the height equal to? 103. 103. I was talking about sines and cosines and those curves. So you would take your middle, your D, your 53, and then add your 50. You're at 103 feet above the ground. And so you can go ahead and set equal to 103 to solve. And then it asks, if the ride is 160 seconds, how many times will you be at the top? Well, we notice back here that you're going to be at 53 at 8 seconds, and then again at 24 seconds. You were at the top one. You could keep going and saying like, oh, add another 16, add another 16, add another 16. You could see how many times you passed the top. That's one way of doing it. That's like a very problem solving, I don't want to do the math kind of way. You end up actually passing it 5 times. Because a whole cycle is 32 seconds, there ends up being 5 different times that you will pass. All right. I know you didn't like the Ferris wheel problem, but it gives you at least a little bit practical application as to what we're doing. Cool, kids. Do you have any questions on the odds? you have any questions on the odds? Specifically, why am I not saying the evens? Because some of you just saw the solutions and realized you were totally off. So you can take a little bit of time, maybe look at the video, maybe look at the solutions, compare, and then come ask me questions. But odds, you knew the solutions too from Calc Chat. So Jason, what's up?
23 and 50.
23 and 53. Are there any other solution or questions? 37.
75.
Okay, let's start with 23. So we're going Jason, Jason, Joe, and then Joe. 23 ended up giving us, oh, Jason, you got it. We're solving, and so I think by them not giving us an interval, we're going to say all. 23, it's factored, so what do you do to each of these? Set equal to 0. So when does sine equal 0? If you're looking at what it should be, that's going to happen at 0, pi, 2 pi, 3 pi, so pi n. Then when will sine equal -1? It actually ends up being the same as that one we were just doing, which will be at 3 pi over 2. So pi n and 3 pi over 2 plus 2 pi n. Is that cool? Cool. What was the other one, though, you had? 37?
That was Joe's.
Oh, that was yours. Let's go pick that one up then. 37. Based on what we did today, I might not do the whole thing, but what do you guys think we should start with? You plugging in stuff? How similar is this to our homework spiral work?
Really similar.
Check it out. I think it'll be super similar. But yeah, otherwise you would have been lost because you're like, I don't know what to... Because homework spiral was hard, right? All right, so this one's hard. Try it with the homework spiral now. Jason, what was your other question?
53.
53. Great questions so far. We just happened to already kind of answer some of them in our work today, which is perfect. Don't worry, you're good. Just get it turned off. Hey, we're allowed to use our graphing calculator. Long story short, Jason, if you tried to solve it by hand, it'd be impossible.
No, but the graph is kind of...
Okay, I get it. Did they give us any sort of interval as far as where 0 to 2 pi? So make sure, number 1, you're in radian mode. Number 2, make sure your x min is 0 and your x max, you know what I'm talking about, in the window, right? Perfect. Then I would have made this guy my y1, and I'm looking for zeros, and zeros are the same thing as x-intercepts. But remember, we have that really cool second trace 0 feature from our Precalc graphing handbook that we can find zeros. So I'm going to get just a quick picture really fast doing that in my calculator. My window is set from 0 to 2 pi. We have to be in radian mode or else everything's going to be off. I'm plugging in my x tangent of x just to make sure we have the same picture. And I end up with that's what I see. And so as long as the 0 and 2 pi are allowed to be included, which, in the interval, I think they meant to put a parenthesis there. So 0 and 2 pi I don't think are supposed to be included, which means I'm not going to look at the 0 on 0. I'm not going to look at the 0 at 2 pi. My guess, just knowing the symmetry, like if that's 2 pi and that's 0, I'm guessing that's pi. But I'm going to go ahead and go do my second trace, my 0 feature, go a little before, a little after. It should be 3.141592. There it is. So my 0 is just the 1, 3.1415926. Is that cool? Yeah, but solving that one by hand is impossible, so you definitely need to go to your calculator. Joe, 75. Where's he at? Oh, down here. Oh, too far. Approximating solutions. This is a lot like what we just saw with the quadratic formula, right? Okay, you're going to have to use your graphing calculator at some point, so how do you use it? I'm going to jump to where we're solving after using the quadratic formula, since we just talked about that. So we're going to end up with tangent. P.S. If you guys noticed, there's an x min that's different and an x max that's different. Joe, you're good. The graphing window, right? X min, X max. Cool. You're in radian mode, right? Cool. When I plug in, I get negative b plus or minus square root b squared minus 4ac. Oops, nope. All over 2a. So I'm going to make tangent of x my y1. I'm going to make 16 and 3 is 48. 48 and 25 is 60, 73. Ugh. I'm going to make this my y2. And Joe, I'm going to look for intersections where these two hit in this window, and I'm going to find those intersections, and those will be my answers. Does that make sense? Perfect. Great question, though. Find the intersections, and then you're good. Anything else? Perfect. Guys, how close are we to the end of class? Very close. So here's what I need you to do in notes. Oh, if you want to, you can peek at this guy. We would have squared both sides and foiled. It would have been very similar to the one we started class with. And then this one we would have graphed and found the zeros like you saw me kind of do or show to Jason and Joe's questions. This page is not necessary for us to memorize. This is the page I need you guys to get down in notes. Nice thing is the homework was not going to be due tomorrow anyway. And remember how I said there were more formulas coming? Okay, don't stress. Don't stress. 5-4 is actually a nice section because 5-4 we're only looking at these formulas. 5-5 is where tons of formulas come in. Not all that need to be memorized, but still tons of formulas. Some of you guys forgot that this chapter has a formula portion to the test, not just a problem portion. I'm changing the due date to Tuesday because, yes, we don't have school on Monday. We're going to do mostly examples tomorrow. But the nice thing is, before we get to 5-5, where there are tons of formulas, 5-4 just lets us focus on these new formulas. I'm going to talk about tomorrow some tricks to memorizing them. Some of you need to get them in a Quizlet, get them in your formula page that you've been studying or rewriting. Get them on formula cards. Some of you, if you're writing these down, you may as well go to 5-5 and write those down too and be studying. You're going to need to have memorized at least the first 3 sections of formulas in 5-5. There are 6 sections of formulas. We'll talk more about that when we get there. But here's the crazy thing with section 5-4 and 5-5. The only new thing, I guess there are 2 new things. The main new thing are the formulas. The directions are actually all review. The directions are actually all review. Evaluating trig functions is going to be like chapter 4. Simplifying expressions is going to be like 5.1. Verifying identities is going to be like 5.2. And solving trig equations is going to be like 5.3. 5.1, 5.2, and 5.3 said, hey, let's do these types of problems with the easiest formulas possible, the easiest identities possible, the ones you went and looked at last night in homework or today to transform. That box, that chart of formulas were the easiest ones possible, but guess what? There are more formulas out there. So we're not going to learn any new types of problems. We're going to be getting maybe common denominators or simplifying. We're going to be doing t-proofs. We're going to be solving equations. But there are new formulas to consider in addition to the old ones. So here's the dealio. For pretty much both of these sections, I'm going to go fast. We're pretty much just going to be doing, what do you see? Yeah? Look at the next section. Oh, new formulas. Examples. New formulas. Examples. New formulas. Examples. New formulas. Examples. All that's new from here on out are formulas and learning how to use the new formulas to do the old instructions. Does that make sense? Yeah. All right. So maybe review a little bit before tomorrow. 5.1, 5.2, 5.3. What kinds of problems we'll be doing? Get these formulas down and start studying them because the test on the formulas is coming. but not until next week, like the end of next week. You guys, good job, good job. Tomorrow, just examples.